bum, 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 bum. You know, now I can't be wearing the same shirt 2 streams in a row. Catch me chirping. You know what? Should we just be ourselves? Right. Never in here. You did. Yes. Let's go. All right, here we go. Chat's up. Yeah, we're back up on the new chat. We are done with the social stream. That app is trash. Sorry to the devs over at Social Stream, but Streamlabs is just so much better. Even for all the free stuff that's offered, you get alerts, you get chats, you get a lot of free widgets. Honestly, really great product so far from what I've been able to use. Awesome, because now I can have just one account and all my widgets across both my streaming PCs, my MacBook and my gaming PC, just with my one central Streamlabs account. Ooh, we're showing a little chest here. Chill out, Mike. Just with one Streamlabs account, and I can have the links to those widgets to both of them. So it's really awesome. Hey, how's it going? What's going on, Harsh? Tim, what's going on, Graveyard? Yeah, a little bit later today. Just been busy at work. I got off late today. I got hit with unfortunately got hit with a rebuild. One of our products that we released just had some abnormal data in the QC levels. And so, but then they went back and tested my samples, that I passed out on my specs, and everything was fine again, and they retested it and everything. And so honestly, something happened during the filling process. And so, yeah. So kind of weird. We can't pinpoint it to what it actually is. So just to give you, I'm not sure how much detail I can provide, but I have a bulk product that I have a bunch of different batches of, and a couple of the batches were just like 2 out of the like, let's say like 80%. So, I mean, it's only like 20% of the batch was testing. It was failing for this test, and it was abnormal, and they were getting a lot of variability, and so they were doing some digging, and then did some retesting and different sample pulling, and then the ones that did pass failed, ended up passing, and then a different one failed. So they went back, and they kind of asked me what happened in manufacturing, and then I went through my records and everything, and then I went ahead and provided my data and my samples that I still had on hand. Right, I need to get what am I saying, dude? Come on, Mike. Lose my train of thought here. I can't even talk. Gather yourself, chill. It's been a long day. So I gave them my samples that were my final testing samples, and those passed. So something happened in between the fill process. So yeah, it's a little strange. Anyways, also, are you from the US? You excited about Apple 17? Finally 120 FPS. Need to get that money up for iPhone 17. Did they release a thing? I haven't seen it yet. Oh, it launches tomorrow, right? I think I might do it. Is there a launch video? Or is it tomorrow? We're reading about Divide and Conquer right now.
Confirmed from a third-party brand, the famous D brand has fully leaked the iPhone 17 lineup. You can see the
D brand leaked it? No, D brand.
Middle and the extremely thin iPhone 17 Air. I quite like the iPhone 17 Pro's design. The enhanced camera island is looking pretty cool, along with the two-tone finish. This bottom part is actually for the wireless charging.
How do you guys feel about the wide camera? It's kind of like the Pixel now, no?
Of course, orange.
Oh, that blue is pretty cool.
To be the most popular color.
That orange is not that cool. I mean, it's like a traffic cone. It's like a traffic cone. Yeah? Traffic cone iPhone? Oh, if I drop my phone out of my car, good thing it won't get run over. That blue is sweet though. If I upgrade, it'll definitely be... See, I've got... What do you guys have? What iPhone do you guys currently have right now? If you guys have iPhone, are you guys Android users? What is your guys' phone model? Let me know in chat what your guys' phone model is. What's going on, Praga? How's it going? Thanks so much for joining me. So honestly, iPhone 14 Pro Max, one of Apple's best designs in my opinion. iPhone 14 Pro Max, top tier iPhone. It's definitely in there of top 5 iPhones out of the whole lineup. In my opinion, iPhone 14 Pro Max, definitely top tier iPhone. Behind probably the iPhone 6s, right? The iPhone 4s, probably the original iPhone, and then probably the iPhone. A lot of people really liked the 5 that had like the gold with the white barring on the top and bottom. iPhone 15. Yeah. Anyways, I think 14 Pro Max it's like a solid blend of it's like one of the best battery lives for size, for camera, for quality. Like this phone is, I haven't had to upgrade. That's kind of how I measure it, is the length of when you need to upgrade. What's your favorite model of iPhone that you guys think? What are your guys' top, your Mount Rushmore of iPhone models? And in the meantime, I saw this on the old nightstand. I thought it'd be fun to bust this out on stream for the, like, if something happens or something. Anyways, back to the good tunes. Upgrade becomes obsolete. 17 has degraded titanium. I will say the only thing bad about my phone right now is that the battery is starting to, it still says it's like full and good, but in my opinion it's just not. I want it to last a little longer. Alright, we got to begin the study sesh here, boys, so let's get into this today. We're gonna continue on here. We need to read about 10 pages. I'm going to read 4.2 and 4.3 today. We already read 4.1 in the part 1 of this, so let's go ahead and do a little intro for the recording. All right, let me back it up. Back it up. Okay. There we go. Let's do a little intro for the recording here. Let me know how it is, you guys. We gotta start the Twitch. All right, we're live on the Twitch too. Cool. All right. There we go. All right, welcome back, everybody. My name is Michael, and welcome back to the channel. Today we're gonna be jumping back into Introductions to Algorithms, 4th edition by CLRS. We're gonna be jumping back into the 4th chapter. Going to be reading 4.2 and 4.3. Or actually, I don't think I'm going to break it up into different videos. I don't even think we really need to do an intro. So we can probably just continue on because the intro was done in the first video. So I'm trolling. Just giving you guys a little bit of cringe for a problem. What's my battery health? Let's check it. %. Yeah, we starting to dwindle here. We starting to dwindle, and I'm noticing it. I'm noticing it for sure. Okay. Chapter 4 here. Okay. 4.2 Strasson's algorithm for matrix multiplication. You might find it hard to imagine that any matrix multiplication algorithm could take less than O of. Come on, Mike. We can't have an error on the first sentence of the. We can't start it like that. You might find it hard to imagine that any matrix multiplication algorithm could take less than theta n cubed time, since the natural definition of matrix multiplication requires n cubed scalar multiplications. Indeed, many mathematicians presumed that it was not possible to multiply matrices in little o of n cubed time, until 1969 when V. Strasson published a remarkable recursive algorithm for multiplying n by n matrices. Strasson's algorithm runs in theta n log to the power of log 7 time, since log 7 is equal to about 2.8073549. Strasson's algorithm runs in O of n to the power of 2.81 time, which is asymptotically better than the theta n cubed time. Matrix multiply and matrix multiply recursive procedures. The key to Strasson's method is to use the divide and conquer idea from the multiply. Oh my gosh, dude. What is wrong with me, y'all? I'm just struggling to read lately. The key to Strasson's method is to use the divide and conquer idea from the matrix multiply recursive procedure, but make the recursion trees less bushy. We'll actually increase the work for each divide and combine step by a constant factor, but the reduction in business will pay off. We won't reduce the bushiness from the height. Oh my gosh. We won't reduce the bushiness from the 8-way branching of recurrence all the way down to the 2-way branching of recurrence, but we'll improve it just a little, and that will make a big difference. Instead of performing 8 recursive multiplications of n over 2 by n over 2 matrices, Strasson's algorithm performs only 7. The cost of eliminating one matrix multiplication is several new additions and subtractions of n over 2 by n over 2 matrices, but still only a constant number. Rather than saying additions and subtractions everywhere, we'll adopt the common terminology of calling them both additions, because subtraction is structurally the same computation as addition, except for a sign change. To get an inkling how the number of multiplications might be reduced, as well as why reducing the number of multiplications might be desirable for matrix calculations, suppose that you have two numbers x and y, and you want to calculate the quantity x squared minus y squared. The straightforward calculation requires 2 multiplications to square x and y, followed by 1 subtraction, which you can think of as a negative addition. But let's recall the old algebra trick of x squared minus y squared is equal to x squared minus xy plus xy minus y squared, which is abstracted out to this, which equals to x plus y times x minus y. Using this formulation of the desired quantity, you could instead compute the sum of x plus y and the difference of x minus y, and then multiply them, requiring only a single multiplication and 2 additions. At the cost of an extra addition, only 1 multiplication is needed to compute an expression that looks as if it requires 2. If x and y are scalars, there's not much difference. Both approaches require 3 scalar operations. If x and y are large matrices, however, the cost of multiplying outweighs the cost of adding, in which case the second method outperforms the first, although not asymptotically. Strasson's strategy for reducing the number of matrix multiplications at the expense of more matrix additions is not at all obvious, perhaps the biggest understatement in this book. As with matrix multiply recursive, Strasson's algorithm uses the divide and conquer method to compute C equals to C plus A times B, where A, B, and C are all n by n matrices, and n is an exact power of 2. Strasson's algorithm computes the four submatrices C11, C12, C21, and C22 of C from equations 4.5 through 4.8 on page 82 of 4 steps. We'll analyze costs as we go along to develop a recurrence T of n for the overall running time. Let's see how it works. Okay. So Strasson's algorithm for matrix multiplication improves upon the original idea of so what is it? If n equals 1, the matrices each contain a single element. Perform a single scalar multiplication and a single scalar addition, as in line 3 of matrix multiply recursive, taking theta of 1 time, and return. Otherwise, partition the input matrices A and B and output matrix C into n over 2 by n over 2 submatrices, as in equation 4 by 2. This step takes theta of 1 time by index calculation, just as in matrix multiply recursive. Step 2. Create n over 2 by n over 2 matrices, S1, S2, all the way up through S10, each of which is the sum or difference of two submatrices from step 1. Create and zero the entries of 7 n by n over 2 by n over 2 matrices, P1, P2, all the way through P7, to hold 7 n over 2 by n over 2 matrix products. All 7 matrices can be created and the pi initialized in theta n squared time. Step 3. Using the submatrices from step 1 and the matrices S1, S2, all through S10, created in step 2, recursively compute each of the 7 matrix products P1, P2 through P7, taking 7 T of n over 2 time. Update the 4 submatrices C11, C12, C21, and C22 of the result matrix C by adding or subtracting various pi matrices, which takes theta n squared time. We'll see the details of steps 2 through 4 in a moment, but we already have enough information to set up a recurrence for the running time of Strasson's method. As is common, the base case in step 1 takes theta 1 time, which we'll omit when stating the recurrence. When n is greater than 1, steps 1, 2, and 4 take a total of theta n squared time, and step 3 requires 7 multiplications of n over 2 by n over 2 matrices. Hence, we obtain the following recurrence for the running time of Strasson's algorithm: 7 times t n over 2 plus theta n squared. Compared with matrix multiply recursive, we have traded off one recursive submatrix multiplication for a constant number of submatrix additions. Once you understand recurrences and the solutions, you'll be able to see why this trade-off actually leads to a lower asymptotic running time. By the master method in section 4.5, recurrence 4.10 has a solution T of n equals to theta n to the power of log 7, which equals to big O of n to the power of 2.81, beating the theta n cubed time algorithms. Now, let's delve into the details. Step 2 creates the following 10 matrices. This step adds or subtracts n over 2 by n over 2 matrices 10 times, taking theta n squared time. Step 3 recursively multiplies n over 2 by n over 2 submatrices 7 times to compute the following n over 2 by n over 2 submatrices, each of which is the sum or difference of products of A and B submatrices. Right? So you take these values and plug them into here to find products. The only multiplications that the algorithm performs are those in the middle columns of these equations. The right-hand column just shows what these products equal in terms of the original submatrices created in step 1, but the terms are never explicitly calculated by the algorithm. Step 4 adds to and subtracts from the 4 n over 2 by n over 2 submatrices of the product C the various PI matrices created in step 3. We start with C11 equals to C11 plus P5 plus P4 minus P2 plus P6. Expanding the calculation on the right-hand side with the expansion of each P sub I on its own line and vertically aligning each term that cancels out. And vertically aligning terms that cancel out, we see the updated C sub 11 equals to which corresponds to equation 4.5, similarly setting C12 equal to this, updating here, corresponding to equation 4.6, setting C21 equal to this, means that updated to C21 equals to this, corresponds to equation 4.7, finally setting C22 to this, means that updated to C22 equals to, which corresponds to the equation 4.8. Altogether, since we add or subtract n over 2 by n over 2 matrices 12 times in step 4, this step indeed takes theta n squared time. We can see that Strasson's remarkable algorithm comprising steps 1 through 4 produces the correct matrix product using 7 submatrix multiplications and 18 submatrix additions. We can also see that the recurrence 4.10 characterizes its running time. Since section 4.5 shows that this recurrence has the solution T of n equals to theta n to the power of log 7, which is equal to little o of n cubed, Strasson's method asymptotically beats the theta n cubed matrix multiply and matrix multiply recursive procedures. Honestly. The baseline recursive matrix multiplication. So suppose you have two n by n matrices A and B. It's so hot. No, it's I can't have that fan on. It's too loud. Sucks. Okay. You're reading about Strasson's matrix multiplication algorithm, which is famous improvement over the standard divide and conquer approach. Let's break it down step by step in simple terms. Why can't I read, dude? The baseline recursive matrix multiplication. Suppose you have two n by n matrices, A and B. The divide and conquer approach splits each into four submatrices of size n over 2 by n over 2. For example, A is equal to these four submatrices and B is equal to these four submatrices. To compute C, which is equal to A times B, you need 8 multiplications of n over 2 by n over 2 submatrices plus some additions. Right? So you pair up the submatrices, multiply them, and sum all those together. This gives this individual recurrence, which is theta of n cubed. So this recursive version doesn't actually improve the asymptotic complexity compared to the standard cubic algorithm. The idea of Strasson's. Strasson realized, what if we reduce the number of multiplications, even if it means doing more additions? Multiplying matrices is much more expensive than adding them, so even trading one multiplication for a handful of additions pays off. Computing x squared minus y squared, normally 2 multiplications plus 1 subtraction, we have this clever trick that only requires 1 multiplication and 2 additions. You cut the multiplications in half. For numbers, that's meh, but for matrices, it's a big deal. How Strasson reduces multiplications. Strasson found a clever algebraic rearrangement that computes the product using 7 multiplications instead of 8. He defines 7 intermediate products, M1 through M7, each solving multiplications of n over 2 by n over 2 matrices.
You're not that guy, pal. Trust me. You're not that guy. Yeah? Absolutely.
Thank you for the sub. Thank you, sir, the sub. I appreciate you so much. Who is that? Let's make sure we get him a shout out here for the sub. Let's make sure we get you your shout out. So, bro, brada, thanks so much. Thank you so much. You're awesome. Thanks for joining me. Oh, I forgot to flip over the. There you go. So you define these intermediate products, each involving multiplications of n over 2 n over 2 matrices. Then he combines them with additions and subtractions to form 4 submatrices equals to these. So the recursion is now 7 times t over 2 by O of n squared. I don't think it's supposed to be little o. Is it supposed to be little o? Might be, yeah. Why is this better? Using the master theorem, a equals 7 and b equals 2. So the complexity is theta n log base 2 of 7 equals to theta n to the power of 2.807, that's faster than theta n to the power of 3. It's a little bit faster, but for large inputs, right, it'll be way faster, significant. Okay, so improves upon the divide and conquer improves upon approach for n by n matrix multiplication. Okay, so improves upon this. How does it do this? Otherwise, partition A and B into alpha matrix C into just as before. So you partition A and B out into so I'm gonna give it this here. If n equals to 1, then each matrix is just a single number. Multiply the two numbers, add if needed, and return. Constant one time. This is just a base case recursion. Partitioning plus setting up helper matrices. For larger n, split ABC into 4 n over 2 by n over 2 submatrices. So now we introduce 10 helper matrices. Each SI is formed by adding or subtracting one of these submatrices. We'll list all. Okay. Also prepare 7 product placeholders, which will hold the recursive multiplications of size n over 2 by n over 2. Creating all of these and zeroing them out equals to n squared. Because you're touching entries n over 2 by n over 2 matrices are constant number of times. So what are these steps? I'll go. Okay, so then 2n by or power. Okay, so you need 2 n by n matrices, right? Where n is a power of 2. So then we say so if not, pad the matrices with zeros until satisfied, right? Then you say so you have base case, right, is if n equals to 1, going to multiply the two numbers so this is going to be, right, C equals to A times B. cool. So base case, multiply two numbers directly in return. And then there's, okay. My apartment complex has a lot of kids and it's really loud. Okay, so next our steps are to divide the partition matrices. So divide partition the matrices, right? So split A and B into 4 n over 2 by n over 2 subgroups, right? Okay. So split A and B into 4 n over 2 by n over 2 submatrices. Okay. So then, so this would be like this. A equals to A let's take it. Right. Okay, that looks good. So then you're going to form 10. Hey, what's going on, Ray? Mr. Ray. Ray of sunshine. So then you're going to form 10 helper matrices. So form 10 helper matrices. S1 S10. Using sum/differences of submatrices. Using sums/differences of submatrices. Right? So you would take the B1, 2 and minus the B2, 2 from it. So you take that, minus, take those, minus. Okay, so you take the differences of the larger matrices. And then you would also sum them together. B11 and B12 get summed together. B11 minus B22. B21 minus B11. Okay, what? Hey Prism, how's it going? So then, hold on, we'll just say then, I really don't get what this is. Then we're going to so this is step 3. Welcome back in, Prism, my friend. Welcome. How you doing, man? It's awesome to hear from you again. And this is 4. Okay, and then 4 is going to be compute 7 recursive multiplications, P1 through P7, right? Each multiplication here is recursive. So each multiplication here is recursive, reducing a number 2. So I'm gonna ask it here. Hold on, we're not done yet. Jeez Louise. Step 5. Combine results to form C, the output matrix. Compute the 4 quadrants of C. And then combine results to form C, the output matrix. So that's that one. And then step 6, return. Combine C11, C12, C21, C22. Matrix C. Come on. What's the reason I started doing CLRS? I suck at lead code. Oh yeah. And it's kind of like I feel like if I don't read it, a lot of other CS majors, pretty much a large majority of CS majors and people have come across this book in their time as studying, so it's only kind of customary, I guess, to it's kind of our to getting our doing our due diligence, doing our what's it called, getting our reps in, getting our you know. So then I'm gonna say, I'm just gonna make a note here then that says complexity, right, Pardon me. So let me just space these out a little bit. Okay. So let me ask you. My question then is, how did he come up with some of these combinations? Is it just completely not random, but is it specific to this algorithm? Like, how did he decide S1 is equal to B sub 12 minus B sub 22, and S2 is equal to B sub 11 plus A11 plus A12? How did he come up with these additions? I don't see any like correlation. Like, some of them you're not even doing the division, some of them you're not even doing the difference of or the summation on. Like B21 is not even being used as the reducing factor from This is the question people usually have when they first meet Strassen. How on earth did he come up with these weird looking SI and PI combos? It feels like magic because the combinations don't look systematic, but there's actually a structure behind them. Let me unpack. The real goal for ordinary divide and conquer matrix multiplication, you need to compute 8 products. C11, which is equal to A11, B11 plus A12, B21. So A sub 11 plus B sub 11. A sub 12 plus B sub 21. Why is it jumping from... Why is it not doing like B sub 12? You're doing A sub 11 plus B sub 11. You're doing B sub 11, so A sub 12 plus B sub 21. Why? Two scalar multiples can be merged if one. Strassen's discovery was essentially this. Each C sub ij is a linear combination in terms of let's look at one. So P sub 1 is equal to A sub 11 so the first matrix, the first submatrix, first because you divide in half and then you divide in half again. So this is the first division, second matrix. Second division, second matrix. Oh. So you subtract the second divisions together. You subtract the first additions. Oh. Then you, okay, oh. So these subscripts indicate X, Y, where X is the submatrix division and Y is the subdivision count of X. Yes, these subscripts are just labels for quadrants. When you split a big matrix into 4 equal parts, where you have A, the first, it's divided into 2 submatrices, the top row and the bottom row, and then it's divided into 2 additional matrices, the left, right, the bottom left, bottom right. Top left, bottom right. Top right, I mean. So then, you would difference all the even quadrants and sum so you would sum all of the, okay, so you would not difference all the evens, so you would difference quadrant A11. Oh, this is so difficult. So quadrant, so S1 is B quadrant, row 1, quadrant 2. So up in the top right here. Minus this guy. Then S4 is B21 minus B11. S8 is B22, 21 plus B22 minus plus. So you plus adjacents, subtract bottom top quadrants and sum left right. Almost. The add and subtracts are not from the quadrant labeling. They are extra algebraic combinations chose to reduce multiplications, for example. B12 minus B22, top right minus bottom right, right? Top left minus bottom right. Top left plus bottom right. Sometimes it's left right. I just don't get, like, how it just seems random. It does look random at first glance, and that what makes Chat's method so clever, but it's not actually random, it's carefully engineered. I want to compute all 4 quadrants of C with only 7 multiplications instead of 8. So each of the product quadrants is normally a sum of 2 products. So we just expanded out this into its P1 and P2 factors. So he just expanded a trick into its parts, and these are the S and P, etc. Strauss basically took the algebraic idea and expanded it into its matrices. He wanted to reduce 8 multiplications to 7. To do this, hey Mad Max, how's it going? I work as a biochemist. I have a degree in human biology and a minor in chemistry, and I work as a professional biochemist for a biotech company where I make biological controls. I formulate and manufacture them. I guess my title is a formulation chemist, Psi 2. Are these always the same in that S1 equals to B12 less than B22, or is it depend on value? They're always the same. So why is it B12 minus B22? How did he determine these nums? The ultimate goal, Strasson's goal, was to do for each quadrant of the product matrix, right, is the resulting, right, A11 matrix plus the B11 matrix times the B11 matrix quadrant plus the A12 plus the B21. So then let me ask then, when we do n by n, is that not transposing cells? We multiply rows of each A by columns of B for each element C is a dot product. You're not swapping transpose. You multiply rows of A, all the columns, a dot product of C. Example. So then, what is the, so if it's like rows A, X calls B, is it cell by cell, or is it sum of the row by X sum of the column? So I is equal to row of A and J is equal to column of B. K runs over all the elements in that row slash column. what this means in the words. Take row I of A to every row in matrix A, and take every column of matrix B, and multiply every corresponding value of each index together. That sum is a single entry in C, resulting matrix. (15 plus 27 equals to 19. What? Oh, this is the sum. (37, 42 equal 19. Anybody have any idea what's going on here? Step 1, compute C11. It goes to A11, B11, B21, A1, 2. A11 is equal to 1. A12. What? A is equal to 1. 5. What? How is 15 plus 27 equal to 5 plus 14? I think it's ChatGPT error. Alright, this book is frying my brain, y'all. What's going on, systems admin? Substitution method, how many pages is this one? It's not that long. Okay, I'm gonna read substitution method, then we'll be done for today. Yeah. All right, 4.3. The substitution. All right. 4.3, the substitution method for solving recurrences. Now that you've seen how recurrences characterize the running times of divide and conquer algorithms, let's learn how to solve them. We start in this section with the substitution method, which is the most general of the 4 methods in this chapter. The substitution method comprises 2 steps. Guess the form of the solution using symbolic constraint. Number 1, guess the form of the solution using symbolic constants. Number 2, use mathematical induction to show that the solution works and find the constants. To apply the inductive hypothesis, you substitute the guessed solution for the function on smaller values, hence the name substitution method. This method is powerful, but you guess the form of the answer. But you must guess the form of the answer. Although generating a good guess might seem difficult, a little practice can quickly improve your intuition. You can use the substitution method to establish either an upper or lower bound on a recurrence. It's usually best not to try to do both at the same time. That is, rather than trying to prove a theta bound directly, first prove a big O bound, then prove a big omega bound. Together, they give you a theta bound. As an example of the substitution method, let's determine an asymptotic upper bound of. As an example of the substitution method, let's determine an asymptotic upper bound on the recurrence t of n equals to 2t of the floor of n over 2 plus theta n. This recurrence is similar to the recurrence 2.3 on page 41 for merged sort, except for the floor function, which ensures that t of n is defined over the integers. Let's guess that the asymptotic upper bound is the same t of n equals to O of n log n and use the substitution method to prove it. We'll adopt the inductive hypothesis that t of n equals to c times n log n for all n that are greater to or equal to n naught, where we'll choose the specific constants c is greater than 0 and n naught is also greater than 0. After we see what constraints they need to obey, we can establish this inductive hypothesis. Oh my gosh! If we can establish this inductive hypothesis, we can conclude that t of n is equal to O of n log n. It would be dangerous to use t of n equals to O of n log n as the inductive hypothesis because the constants matter, as we'll see in a moment in our discussion on pitfalls. Assume by induction that this bound holds for all numbers, at least as big as O naught and less than n. In particular, therefore, if n is greater than 2 times n naught or equal to it, it holds for floor of n over 2, yielding t of floor of n over 2, which is less than some constant c times the floor of n over 2 times the log of the floor of n over 2. Substituting into recurrence 4.11, hence the name substitution method yields that t of n is less than or equal to 2 times some constant c times the floor of n over 2 times log floor n over 2 plus theta n, which reduces down to theta t of n is equal to, which reduces down to t of n is less than or equal to c n log n, where the last step holds if we constrain the constants n naught and c to be sufficiently large that for n greater than or equal to 2 times n naught, the quantity cn dominates the anonymous function hidden by the theta n term. We've shown that the inductive hypothesis holds for the inductive case, but we also need to prove that the inductive hypothesis holds for the base case of the induction, that is, that t of n is less than or equal to c n log n when n naught is less than or equal to n, which is less than n naught times 2, as long as n naught is greater than 1, a new constraint on n naught. We have log n is greater than 0, which implies that n log n is greater than 0. So let's pick n naught equals to 2. Since the base case of recurrence is not stated explicitly by our convention, T of n is algorithmic, which means that T of 2 and T of 3 are constant, as they should be if they describe the worst case running time of any real program on inputs of size 2 or 3. Picking C equals max of the set T of 2, T of 3 yields T of 2, which is less than or equal to C, which is less than 2 log 2 times C, and T of 3, which is less than or equal to C, which is less than 3 log 3 times C. Establishing the inductive hypothesis for the base cases. Thus, we have T of n is less than or equal to C times n log n for all n that are greater than or equal to 2, which implies that the solution to recurrence 411 is T of n equals to big O n log n. In the algorithms literature, people rarely carry out their substitution proofs to this level of detail, especially in their treatment of base cases. The reason is that for most algorithmic divide and conquer recurrences, the base cases are all handled in pretty much the same way. You ground the induction on a range of values from a convenient positive constant n naught up to some constant n naught prime, which is greater than n naught, such that for n is greater than or equal to n naught prime. The recurrence always bottoms out in a constant size base case between n naught and n prime naught. This example used n prime naught, which is equal to 2 times n prime, or n naught. This example used n prime naught of 2 n naught. Then it's usually apparent without spelling out the details that with a suitably large choice, Then it's usually apparent without spelling out the details that with a suitably large choice of the leading constant, such as C for this example, the inductive hypothesis can be made to hold for all values in the range from n naught to n prime naught. Interesting. So it's kind of just going over how you can use the substitution method to use that inductive proofing technique in math to kind of show with a good general guess to, okay, if I'm going to kind of guess the answer, it's kind of like plugging and chugging almost. I'm going to kind of guess a running time for this algorithm and kind of back calculate based on that to see if it kind of checks out for some values of n. And it kind of gives you a technique here of choosing some values of n naught and n prime naught to prove this mathematically, right? Making a good guess. Unfortunately, there is no general way to correctly guess the tightest asymptotic solution to an arbitrary recurrence. Making a good guess takes experience and occasionally creativity. Unfortunately, learning some recurrence solving heuristics as well as playing around with recurrences to gain experience can help you become a good guesser. You can also use recursion trees, which we'll see in section 4.4, to help generate good guesses. If a recurrence is similar to one you've seen before, then guessing a similar solution is reasonable. As an example, consider the recurrence T of n equals to 2t of n over 2 plus 17 plus theta n. Define on the reals. This recurrence looks somewhat like the merge sort recurrence 2.3, but it's more complicated because of the added 17 in the argument to t on the right-hand side. Intuitively, however, this additional term shouldn't substantially affect the solution to the recurrence. When n is large, the relative difference between n over 2 and n over 2 plus 17 is not that large, but both cut n nearly in half. Consequently, it makes sense to guess that T of n is equal to O of n log n, which you can verify is correct using the substitution method in this exercise. Another way to make a good guess is to determine loose upper and lower bounds on the recurrence, then reduce your range of uncertainty. For example, you might start with a lower bound of T of n equals to big omega of n for recurrence 4.11. Since the recurrence includes the term theta n, you can prove an initial upper bound of T of O of n squared, then split your time between trying to lower the upper bound and trying to raise the lower bound until you converge on the correct asymptotically tight solution, which in this case is T of n equals to theta n log n. A trick of the trade. Subtracting a low-order term. Sometimes you might correctly guess a tight asymptotic bound on the solution of a recurrence, but somehow the math fails to work out in the induction proof. The problem frequently turns out to be that the inductive assumption is not strong enough. The trick to resolving this problem is to revise your guess by subtracting a lower order term when you hit such a snag. The math then often goes through. Consider the recurrence. T of n equals to 2 times t of n over 2 plus theta of 1. Define on the reals. Let's guess that the solution is t of n equals to big O of n, and try to show that t of n is less than or equal to c times n for n which is greater than or equal to n naught, where we chose some constant c and n naught to be greater than 0 suitably. Substituting our guesses into the recurrence, we obtain this inequality where t of n is less than or equal to 2 times c times, oh my gosh, we have this inequality. T of n is less than or equal to 2 times c times n over 2 plus theta 1, which equals to c times n plus theta of 1, which unfortunately does not imply that t of n is less than or equal to c of n for any choice of c. We might be tempted to try a larger guess, say t of n is equal to big O of n squared. Although this larger guess works, it proves only a loose upper bound. It turns out that our original guess of t of n equals to O of n is correct and tight. In order to show that it is correct, however, we must strengthen our inductive hypothesis. Intuitively, our guess is nearly right. If we are off only by theta of 1 in a lower order term, nevertheless, intuitively our guess is nearly right. We are off by a theta of 1, a lower order term. Nevertheless, mathematical induction requires us to prove the exact form of the inductive hypothesis. Let's try to trick our subtraction. Let's try our trick of subtracting a lower order. Dude, what is going on? Come on, Mike. Let's try our trick of subtracting a lower order term from our previous guess. T of n is less than or equal to c times n minus d, where d is greater than or equal to 0, is a constant. We now have this, which is equal to c times n minus 2d plus theta 1, which reduces down to t of n is less than or equal to c times n minus d. As long as we choose d to be larger than the anonymous upper bound constant hidden by the theta notation, subtracting a lower order term works. Of course, we must not forget to handle the base case, which is to choose the constant c large enough that c times n minus d dominates the implicit base cases. You might find the idea of subtracting a lower order term to be counterintuitive. After all, if the math doesn't work out, shouldn't you increase your guess? Not necessarily. When the recurrence contains more than one recursive invocation, if you add a lower order term to the guess, When the recurrence contains more than one recursive invocation, if you add a lower order term to the guess, then you end up adding it once for each of the recursive invocations. Doing so takes you even further away from the inductive hypothesis. On the other hand, if you subtract a lower order term from the guess, then you get to subtract it once for each of the recursive invocations. In the above example, we subtracted the d constant twice because the coefficient of t of n over 2 is 2. We ended up with the inequality t of n is less than or equal to c times n minus d minus theta of 1, which we readily found a suitable value, and we readily found a suitable value for d. Avoiding pitfalls. Avoid using asymptotic notation in the inductive hypothesis for the substitution method because it's error-prone. For example, for recurrence 4.11, we can falsely prove that t of n is equal to big O of n if we unwisely adopt that t of n is equal to O of n as our inductive hypothesis. So that means that puts here t of n is less than or equal to 2 times big O of n of the floor of n over 2 plus theta n. which reduces down to this. The problem with this reasoning is that the constant hidden by the O notation changes. We can expose the fallacy by repeating the proof using an explicit constant. For the inductive hypothesis, assume that T of n is less than or equal to C times n for all n values that are greater than or equal to some n naught, where C and n naught are greater than 0 and are constants. Repeating the first two steps in the inequality chain yields this, where T of n is less than or equal to 2 times C times the floor of n over 2 plus theta n, which is less than or equal to C times n plus theta n. Now indeed, C times n plus theta n equals to big O of n. But the constant hidden by the O notation must be larger than C because the anonymous function hidden by the theta n is asymptotically positive. We cannot take the third step to conclude that C times n plus theta n is less than or equal to C times n, thus exposing the fallacy. When using the substitution method, or more generally, mathematical induction, you must be careful that the constants hidden by the asymptotic notation are the same constants throughout the proof. Consequently, it's best to avoid asymptotic notation in your inductive hypothesis and to name constants explicitly. Here's another fallacious use of the substitution method to show that the solution to recurrence 411 is T of n, which is equal to O of n. We guess T of n is less than or equal to C times n, and then argue that the recurrence T of n is less than or equal to 2 times C times the floor of n over 2 plus theta n, which is less than or equal to C times n plus theta n, which is O of n. Since C is a positive constant, the mistake stems from the difference between our goal, to prove that T of n is equal to O of n, and our inductive hypothesis, to prove that T of n is less than or equal to C times n. When using the substitution method or in any inductive proof, you must prove the exact statement of the inductive hypothesis. In this case, we must explicitly prove that T of n is less than or equal to C times n to show that T of n is equal to O of n. Interesting. Interesting. So I definitely want to... That was the end of 4.3 in chapter 4. Going to go over this. Let me break this down in simple terms. This is a common mistake when using the substitution method to prove the complexity of a recursive algorithm. What the substitution method is. The substitution method is a way to prove the runtime of a recursive function by 1. Guess a bound for T of n T of n is equal to big O of n, or T of n less than or equal to C times n. For some constant C. 2. Use mathematical induction to prove that the guess is correct. What the fallacy is? The text is pointing out a common mistake. People sometimes write something like this, where the recurrence is less than or equal to 2 times the recurrent times t of n over 2 plus, so the next recurrence down, plus f of n, which is less than 2, equal to 2, times c times n divided by 2 plus f of n. What in the world? Then they immediately say this. The mistake, they are changing constants implicitly. The c in the inductive hypothesis may not be large enough to cover the extra f of n. You just gave me some long expression or inequality without explaining any of it. When you have a recursion runtime like this, right, the substitution method works like this. You guess the solution. I think the recursion grows linearly. N, right? You use induction to prove the guess is correct. People do this. They guess that it's O of n. They plug it into the recurrence. So if our recurrence was originally this, right, we plug for t of n over 2, we plug in O of n over 2, which gives us to the 2's reduced, gives us to O of n plus n, which equals to O of n. Then they declare, oh, we're done, t of n equals to O of n. Why it's wrong. The O of n hides a constant factor. Maybe the actual constant you need is bigger than the one you assumed. So they're assuming a constant factor of 2 here, right? Think of it, you say that each step costs less than or equal to some constant times n. You have to make sure that the constant works for all steps. You can't just hide it in O of n and hope for the best. How to do it correctly? When you write the guess with the constant, t of n is less than or equal to c times n. Use induction to figure out what value of c works. Only after the proof is complete can you say that it's O of n. Okay, so let's see an example here. Hey, force of nature, yeah, that's exactly kind of my reasoning for it. Even though it's difficult and it has a lot of math kind of notation and it might be challenging, I wanted to challenge myself and push through. And I know that by pushing through this and coming out on the other side, it'll just set us up even better for things like leak code and our own projects. So, yeah. Suppose that we have this recurrence, right? And we want to prove that it's O of n. So we make a guess that t of n is less than or equal to c times n, right? Or some constant c we will choose, where some constant c we will choose. So we plug it into our inductive hypothesis. So if this is the value we're trying to substitute, t of n over 2, right, which is less than or equal to c times n over 2, then we can plug that right into here, right, as such. Which is less than or equal to 2 times c so it's just so it's just this, and then the upper bound so this is putting in the upper bound to solve for c when true. The core of the substitution method, you guess the upper bound, plug that into the recurrence. This gives you this. Now you check if the inequality is actually true for the chosen c. If it's not, you adjust c so that c times n plus n is less than or equal to c plus n holds. Huh. Interesting. Cool. All right, so that was section 4.2 and 4.3 out of chapter 4. We're going and breaking up chapter 4 as it's kind of a longer chapter. We're only on page 95 here, and chapter 4 doesn't end until right here, page 124. So another 30 pages. So maybe we'll do another 15, and then we'll call it there. These are just too dense to do all at once, or man, brutal. Anyways, you guys, thanks so much for being here and hanging out for this reading in chapter 4 for today. Appreciate you guys being here and joining me. My name is Michael. We did a 3,000 subscriber special yesterday where we opened up some cases and played some games in Counter-Strike. If you guys didn't check that out, feel free to check out the VOD. It's a lot of fun. We'll be doing that, periodically as we hit milestones on the channel, open up some cases and play games. But I'm also considering, like on Friday nights, potentially playing some games behind kind of like the channel membership, unlocking that feature of the channel, but keeping all the main core content related to programming completely free. But also having free gaming streams at our milestone marks, because the main purpose of this channel is not gaming and not really leisure. It's grinding, it's focusing on programming, it's building stuff and learning. But obviously sometimes it's fun to take a break when we hit certain goals to reward ourselves. So anywho, I appreciate all the new people that stopped in today. My name is Michael. I'm 26 years old. I got a degree in human biology and a minor in chemistry, and I work as a formulation chemist for a biotech company since I graduated back in 2021. And I've been teaching myself how to code and programming and computer science topics for the past year and a half now, going over various things like you see on the screen, reading books, doing courses like CS50, MIT OpenCourseWare, and the like. If you guys have enjoyed this video, please leave a like, and it really helps to keep our channel, kicking. And truly thank you guys so much for being here. You guys can get access to these notes in my GitHub. Let me push them up here. Right. Cool. So I am chopping up these streams and posting kind of like audiobooks, visual audiobooks, I guess. I'm cutting out all of the the GPT researching, the stumbling, the stutters. I'm cutting out all that stuff just to have a fluid read throughout the entire chapter. I've gotten up through chapter 2 posted so far. I need to chop up and edit my chapter 3. and then obviously chapter 4 as we finish this one. But so go back and refer to those videos if you're wanting to get kind of follow along to someone else's reading if you struggle to read on your own. And yeah, thank you guys so much for being here, and I'll see you guys tomorrow, where we'll continue on. Tomorrow we'll probably, honestly, we need to kind of wrap up. We really need to just get it done and just wrap up the problem set 3 for MIT OpenCourseWare 60002. So we're taking the 6.0002 course right now, which is the Introduction to Computational Science and Introduction to Computational Thinking and Data Science, which kind of leads and is a precursor into machine learning. So it's a great course, and we're on problem set 3 and week 8 of that course. So we need to finish problem set 3 and just sit down and just get it done. So it's not the most fun stuff to do. It's homework, but we got to do it, guys. So that's probably what we'll end up working on tomorrow, and then kind of get back working on some of our projects too after that. So thank you guys so much for being here tonight. Let me know what you guys are working on. Please join my Discord and chat with me there. Yeah, guys.